Recordings rolling. It's Monday, November 17th. So here's top mathematician for Module 5. So Humpty John, you made the list. Top mathematicians. Yeah, top mathematicians. Nice job, Dave. Okay. So starting module 6 today, lesson 6.1, operations on polynomials. Okay. And then I have open for you guys, Alex, 6.1, 6.2, 6.3. So we'll cover 6.2 tomorrow and then 6.3 on Wednesday. Okay. And then have this due by the end of Friday. Okay. And that'll take us to Thanksgiving break. So what's in 6.1? Operations of functions. What is module 6? So module 6, well, the title of module 6 is inverse and radical functions. Yeah. Okay. So 6.1, operations on functions. We're looking at function addition, subtraction, multiplication, and division. And then there's these composite functions. Do you see this where you take one function and feed it into another function? So you have f of g of x or g of f of x, right? Which could result in different values. Right? So here, I'll do some examples with you guys. Here, on the first page, they give you addition, subtraction, multiplication, division. And then if you flip a couple of pages, they talk about composite functions, like what is f of g of x or what is g of f of x. Okay. So there's some fun examples here. I'll give you guys one example of a composite function that shows it later in the book. Is there's somebody trying to get the best discount on something. They can get a 20% discount and a $5 off coupon. Right? They say, oh, well, you can actually use both. So should you apply the coupon first and then the discount, or the discount first and then the coupon? Okay. So it's like, should you do g of f or f of g? Right? Which one will save you more money? Right? There is an answer to that. So definitely. But here, I'll do real straightforward, guys. Let's do how about number 1 straight out of the book? Right? They give you a couple of functions. Okay. So I'll write down the functions here. So f of x is 2x. Sorry. F of x is 2x. Okay. And then g of x, they're giving us negative 4x plus 5. Right? So somewhere they might throw in also an h of x into the mix, or they could turn this to a word puzzle. Right? So there could be some real world application, interpretation of this. Okay? Let's get these functions. Right? And what can I do with all these functions? Well, let's try all 6 of these things. All 6 of these. Add, subtract, multiply, divide, and then what's f of g and what's g of f. But we'll try all of these things. Okay? So let's start by addition. Addition. So f of x plus g of x. Well, that would be 2x plus negative 4x plus 5. Okay? And then you just very simply combine like terms. Here, both of these have an x term in common. So you can add those two together. And it would look like that. Right? That's f plus g. Sometimes you might see it like this, f plus g of x, if you see that notation. Right? So there's addition. How about subtraction? Subtraction. So what's f of x minus g of x? Okay. Well, this is really similar. So it'd be 2x minus and then negative 4x plus 5. Okay. Now you could distribute this negative. So guys, if you subtract negative 4x, it's that same thing as adding 4x. So wouldn't that give you 6x? Okay. And then it would subtract off this 5, so minus 5. Okay. And notation you might see for that might be like f minus g of x. Right? So keep in mind this notation on the left side is not multiplication, it's a function notation. So it's like f plus g of x or f minus g of x. Same thing as f of x minus g of x. Okay, so that's addition, addition, subtraction, you can very simply combine like terms. So that's not bad. Okay. Let's try multiplication.
Wait, can you go back to subtraction?
Subtraction? Yeah.
You just keep it out. Great. What is it mean by f of g? You know, in addition.
Okay, so addition. F of x plus g of x.
No, you wrote f of the plus you
Oh, f plus g of x is the same thing as this. This and this are the same thing. And this are the same thing. Like, it's just different notation. Yeah, so if you ever see like, yeah, one function minus another function, like of x, it's just one function minus the other function. That's about minus g of x. Okay. right, so you guys got addition, subtraction, just combine like terms. Right, if they each had an x squared term, you could add or subtract those from each other. Okay. Okay. All right, let's do multiplication. Multiplication. So what is f of x times g of x? Well, that would be, I know f of x is 2x. I know g of x is negative 4x plus 5. Okay. And then I can just distribute. So this distributes into each of these terms. So that'd be 2x times negative 4x is negative 8x squared. And then plus 2x times 5 is 10x. Like that. Okay. And that notation you might see f times g of x. It's the same thing. Same. So that could be that. Right, we're just multiplying the two functions together. Okay. How about division? Alright. And of course, division, you could divide either way and you would get different answers. So what if I do f of x divided by g of x? Okay. That's 2x divided by negative 4x plus 5. Okay. Now, guys, does that simplify it all? Can I say, oh, I can cancel out the x? Can I cancel out the x? No, I can't do that. Because I have different terms in the denominator. Okay. Now, if it was the other way around, then maybe I could. Here, I'll do that one with you guys too. This could be f over g of x, which is like that. What if I do it the other way? What if I do g over f of x, which is the same thing as g of x over f of x? Right, so this is different. What if I do negative 4x plus 5, and this is all divided by 2x? Now, you could leave it like that. That should be fine. But you could also break this one into two separate fractions. You couldn't do that with f over g, but you can do that with this g over f. It's going to separate this like this plus this. So it could be negative 4x on 2x, and then plus 5 on 2x, which could negative 2 plus 5 on 2x. Okay. So that could also be that. All right, you guys good with multiplication, division? Yes. Multiply the functions together, divide the functions. I divided them two different ways to get two different answers. Yeah. This is f over g. This is g over f, which could also simplify to that. Okay. All right.
Wait, so that has to help.
Yeah, guys, this would have a vertical asymptote at x equals 0. You uh, could not have a x equals 0. Now that's for g over f. Okay? Now f over g looks like it also has a vertical asymptote. What would that be at 5 over 4, I think? 1.25? Because if you plugged in 5 over 4 for x, 1.25 for x, then wouldn't this whole denominator work out to 0? Which would also give you a vertical asymptote. Yeah. Okay. So yeah, these two graphs are different from each other. F over g and g over f are two totally different things. Yeah. Each have their own vertical asymptote. All right, guys, good with multiplication division? What's that? Okay. So last parts here, composite functions. Composite functions. Okay. So you might see that like sometimes you see this notation, FOG of X. Okay. Sometimes it's called like fog. So that open dot right there, that open circle dot, right, really means you're creating this composite function, which actually I prefer this notation myself of g of x. Okay. So whatever g of x is, you just plug that in everywhere you see x for f of x. Okay. But you can also make a composite function the other way. So I'll do both with you guys. So let's start with this one. So f of x is 2x. So f of g of x would be 2 times, and then instead of x, I'll say g of x. And g of x is this whole expression right here. Negative 4x plus 5. Is that? Okay. See, it's where the x was for f of x, I just popped in g of x. So I'm taking f of g of x. Okay. And then you could clean this up. So this one, it looks like I can distribute the two, because this does multiply, right? This really means 2 times that. Okay. So f of g of x is negative 8x plus 10. Like that. Okay. Or you could go the other way. Right? What if you had g of f of x, which is like g of f of x, right? Well, now I'm just going to do the opposite. I'm going to take f of x and substitute that in everywhere I see an x for g of x. Right? So g of f of x goes, well, g of anything is negative 4 times that thing plus 5. Is it like that's the model for g of x? Okay. And in brackets here, where you normally put in x, instead I'm going to put the entire function f of x, which pretty simple function is just 2x. So that's where that would go. Okay. But if this was more complex, like if this was an x squared, then I have to square out that whole term or something like that. Okay. Great. So just everywhere in x is, I'm just going to swap the whole function f of x. Okay. And this turns out to be negative 8x plus 5. Right. Notice that these came out different than each other, right? And they usually do. Right. They don't have to necessarily, right? But they usually do. So that's a, okay. So g of f and f of g could be 2 different things. Right? Guys for those? All right. Okay, I'm gonna point out at least a couple of word puzzles that I like a lot. Right? That are again in the main video. So right? So I'll roll that in the background too, right? Um, yeah, here. Right, so got Sporting Goods stores offering a 20% discount on shoes. And we got Mariana also has a $5 off coupon that can be used with a purchase. She's planning to buy a pair of shoes that will cost they originally cost $89. So that's the pickup price. Right? Well, the final price will be lower if the discount is applied before the coupon or if the coupon is applied before the discount. Okay? What would that be? Here, I'll go ahead and do this with you guys. So this is number 18. This is an example of a composite function. So the original price is $89. Okay. If she applies a discount, I'll say discount is the function of x. Guys, if it's 20% off, that means you actually pay what percentage? 80%. Could that be 80% of any price? Right. And the coupon function just says $5 off. So it's whatever the price is minus $5. Is that true? So this is like discount as a function of the price, and this is the coupon as a function of the price. Okay. What do you pay? Right. So she apply the discount or the coupon first. Okay. If she applies the discount first, then coupon. Well, that would be like coupon of discount of the discount price, okay? Which should be the discounted price minus $5 after the fact. Okay? So that'd be like 0.80 times the original price minus $5 after the fact. Okay? But if she does coupon first, then discount, well, that would be like discount of a coupon price, right? Which would be you take $5 off first, and after the fact, you multiply by 80%. So it'd be 80% of x minus 5, which is the same thing as you could distribute that 80%. Guess what's 80% of 5? Like 4, wouldn't it? Right. So then you can take whatever the list price is. They said that $89 was the original value. That takes the place of this x here. Yeah, or like here. Right. Then you can figure out how much would you pay for that pair of shoes in this case. Okay. Yeah. Right, that's it. And then you can compare. What should I do first? Should I do this first, that first? Okay. And I'll do one more with you guys here, which is 37. The volume of a balloon with radius r is given by 4/3 pi r squared. So that would be the volume of the sphere based on its radius. The balloon is being inflated so that the radius increases at a constant rate. So 1/2 t plus 2. Okay. They want you to figure out what's the volume of the balloon as a function of time, which is also an example of a composite function. So here's your weather balloon. It's 3D. It's got some radius r. Okay, and I know the volume of the sphere, in this case the balloon, is 4/3 pi r cubed. Right? Isn't that the radius of a sphere? Radius of a spherical weather balloon. Okay. Okay. No, that's volume is a function of radius. Maybe I should do that. V is a function of r. Okay. But they're also pumping this up. We got radius as a function of time is 1/2 t plus 2. So maybe at time 0, it was already 2 meters large, right? And then as time is passing, we're maybe every second we're increasing that radius by 1/2 meter. So the question is, what is volume, not as a function of radius, but as a function of time? So after like 3 seconds of pumping this up have passed, what's the volume? Oh, well, that's the same thing as volume is a function of radius, is a function of time, which should be a composite function. Yeah, like that. You could call that v of r of t. Right? You might also see that notation. All right, so let's put it all together. So volume as a function of time could be, I got it 4/3 pi. And then it's radius to the power 3, but radius is this whole function right here. I'm gonna pop that in place of radius. I'm gonna put, well, in terms of how much time has passed, it's 1/2 t plus 2. Okay. And that's all being raised to the power of 3. Ah, you guys see that? Raised to the power of 3. Okay. Now, you could expand this out with, do you guys remember Pascal's triangle? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Okay. So you could totally expand this out. Might take a little bit of time. Actually, I'll show you guys what the answer is, because I think you guys get the idea how to solve that. Okay, so we are on 6y. 7. Okay. So when you expand it all out, you should get volume as a function of time is, let's see. So I'm copying this out of the teacher's edition, but it does look right, I think. It's like this plus 2 pi t squared plus 8 pi t plus 32 over 3 pi. Yeah, something like that. Right? And see now with this, and this could be the same thing. So if Alex asks you this question, I bet you could type in either one and she could be full credit. Right? But with either one of these, you can plug in, say like 3 seconds have passed. Just plug that in, and it'll tell you exactly what is the volume of the balloon. Right, so there you go. There's composite functions.